We've covered sets, so now we'll take a look at what we can do with sequences. What if order matters? Sometimes the order of items in a collection does matter. We've considered sets up until now where order doesn't make a difference. The set 1, 2, 3 is the same as the set 2, 3, 1. But sometimes it does matter. Order is an important thing. In various situations, that order really matters. So we can think of a few. Names on a wait list. If I'm next in line, I want to know that that's captured. I don't want to be treated the same as somebody that arrived last. Items on a prioritized to-do list. We can think of a to-do list when we think of sets, where we have a list of things to get done and we don't place a priority on one over the other. We just need to cross them all off to complete our tasks. But sometimes we need to prioritize. We have too many things on the to-do list, and so we have to put them in an order that makes the most sense to accomplish. As students, you're probably doing this all of the time. The list of books on an organized bookshelf. Can you even imagine a library without an order? So enter sequences. A sequence is known sometimes as a list or a tuple, and it's just an ordered collection of objects, and that's what matters in this. It's an ordered collection of objects. And we represent this using these angle brackets, and we write them out, the elements that are making up this sequence in order. So A1 comes before A2, followed by A3, and so on. So for instance, the cities I might visit from Halifax to Sydney, Cape Breton, would be Halifax, Truro, Antigonish, then Sydney. And we would follow in that very specific order. The order would matter. Bits, we've seen here's a sequence of bits, 0, 1. This is different than the sequence 1, 0. Whereas sets, that order didn't matter. In a sequence, the order does matter. So the sequence 0, 1 is different from the sequence 1, 0. Or a list of names, students in a class in the order that they registered. All of these are examples of ordered lists or sequences. When the number of objects in a collection is small, 2, 3, and 4, we give those sequences a special name. If you have a collection of 2 objects, such as A1, A2, listed here, that's referred to as an ordered pair. 3 objects, an ordered triple. 4 objects, an ordered quadruple. And then anything greater than 4, we just refer to as an n-tuple, where n is the total number of objects in the collection. Let's take a look at a very specific way that sequences are used, and jumping off the page might be a word that you're familiar with, the Cartesian product. So Cartesian is the word that I think might sound familiar, and it might sound familiar because you've made use of it in the Cartesian plane. And this is the plane that you would map points on XY axes. Many people would have done this throughout junior high and high school. And so it's a Cartesian product that is used to create that Cartesian plane. A Cartesian product is something denoted as A cross B, and it's built up from 2 sets, so 2 sets A and B. And the way that you create that is you say A cross B is equal to the set of all of the possible ordered pairs that you can create, where the first element in that pair is from the set A, and the second element in that ordered pair is from the set B. So it's all the ordered pairs where the first component comes from set A, the second comes from set B. This is the same thing that we use to create the Cartesian plane. Let's take a look at what it looks like in general. So if we have a Cartesian product of 2 sets, a set 1, 2, and a set 3, 4, if we cross those, what we're doing is we're saying we want all the ordered pairs where A comes from either the elements 1 or 2, so our first set, and B is one of the elements 3 or 4. And so we look at every possible combination of ordered pairs that can come, that can produce. We get 1, 3, 1, 4, 2, 3, and 2, 4. And that's all that we can generate from those two sets, the Cartesian product of those two sets, because those sets are small. But we've seen a bigger example, and that is the Cartesian plane. There's no limit to the possible combinations of x and y that we can create in that Cartesian plane. And so if we remember that, that's actually the Cartesian product of all of the reals and all of the reals. So what it produces is a set of ordered pairs, x and y, where x can be any real number, y can be any real number. And so we then map these things onto this XY grid. So y is the vertical bit. And so this is y, all these big numbers, positive numbers, negative numbers to the bottom, and x ran from left to right with the positives over on the right and the negatives over on the left. And you've probably had loads of time plotting these things. And so all of the possible ordered pairs that can exist fit on here somewhere. We see here I plotted an arbitrary xy as a point, but maybe you would be asked to map negative 2, comma, -1. And there's an ordered pair. And where that lies is we would look on the grid and we'd say, here's x -1, here's x -2, y down here -1, and we'd follow out on this line down to the place that this is where that point would lie. -2, -1. The number of sequences that make up this set, which we call R squared, or the Cartesian plane, is infinite, right? Where there's no limit to the number of numbers that x can be comprised of, and the same is true for y. We can also represent other sets as a Cartesian product. So let's consider the set of rational numbers. Recall that those rational numbers are just the set of all the numbers of the form n over d, where both n and d are integers. So n is in z, and d is also an integer, but in this case, the denominator d is not equal to 0 because division by 0 is a problem. We can represent those instead of writing them out as a typical fraction. As long as we know which is the numerator and which is the denominator, we can store that information and represent that as a sequence, n comma d. So the first is the numerator, and the second in the sequence is the denominator. And so this is one possible way to represent the rationals. It's z cross all those integers z not equal to 0. And what this is going to give us is a set of so many things. So it will contain things like -5, 3. It will contain a 0, 1. It will contain 3, 1. And it will contain 5, 3. And infinitely more possibilities. But these are some of the elements that would be in there. And in fact, it'd be every possible combination of integers and integers not equal to 0. So what does that represent? Well, -5/3 represents -5/3. Zero over 1 represents the fraction 0/1, but that's the same as 0, right? 3, 1 represents the fraction 3/1, which is the same as 3, the integer 3. All of these are rational numbers, and in fact, that shows that integers are a subset of the rationals. the fact that we can represent every integer as a fraction with 1 as the denominator. And then our final example is a representation of 5/3. And that's just 5/3. Okay, so these are ways that we can represent information. Another example of how we make use of sequences and in fact the Cartesian product in crafting possible sets of what values can take on would be when it comes to the colors depicted on your screen, for instance. So these are called RGB colors, where the R stands for red, the G stands for green, and the B stands for blue. And we typically represent those as an ordered triple. And that ordered triple, represented here as the sequence RGB, allows the values R, G, and B to range from 0 to 255. And the way that we craft that landscape of ordered triples that these values can take on is we look at the Cartesian product of the set 0 to 255 crossed with the set 0 to 255 crossed with the set 255. And what you end up with, aside from the other way that we can represent that is 0 to 255 cubed, you'll see there, what we end up with is the set containing all the possible ordered triples that the combination of red, green, and blue can take on. So we would see 0, 0, 0 in it, 0, 0, 1, 0, 1, 0, all the way up to 255, 255, 255 as an ordered triple. And that's it for sequences. The next stop is functions.
I feel like I need more information to function properly.
Good news. Our next topic is functions.
Oh, great. See you next time.
See you next time.
I didn't know. I should have said, oh, great, like it's a good thing or a bad thing.